everybody. My name is Narihiro Nakamura. Please call me Nari. Today, I'd like to talk about parallel was CRuby DC. Okay. I'm very happy now because I'm meeting the other attendees here at RubyConf. And one of my dreams is to talk at RubyConf now. So I'm very happy and excited. So today is my first presentation in English. Thank you. My English is not good, but I do my best. Please bear with me. Okay, I'd like to introduce myself with a timeline like this. Before 2005, I was not a programmer. I worked at the ice cream factory. In ice cream factory, I worked in an assembly line. For example, I made many cardboard boxes. I was a professional cardboard box maker. So I made 150 boxes per hour. So I was like a machine. I went to computer school from 2005. I learned the Java language over 6 months. I worked at a computer company since 2006. I used Java then. I worked in a big company. This work was similar to assembly line work. I made a part of product. I didn't understand the whole product. So I was still like a machine. Then I met Ruby. I've used Ruby in my hobby. I changed job. My new company works using Ruby. I have been using Ruby in my work. Currently, I work at NSCL. Mats and Shohei and Takakoji are my co-workers. Shugo is my boss. There are CRuby committers. When I started Ruby programming, I felt free. This work wasn't similar to assembly line work. I could make the whole product. So I was no longer a machine. Then I met garbage collection. DC technology is very interesting for me. This is a garbage collecting machine. I've been creating it since then. It's very fun. So I'm making a machine. Okay, I'd like to talk about my relationship to DC. I'm a CRuby committer. I work on DC. And I wrote a book about garbage collection. But it's only in Japanese, sorry. And I've been creating DC with RDD. So what is RDD? RDD is Ruby Kaigi-driven development. Let me talk about my RDD history. I created long life DC at Ruby Kaigi 2009. Long life DC treats long life objects as a special case. It's similar to generational DC. But long-range DC was rejected in CRuby 192 by some reason. I'm so sad. But long-range DC has been used in Kizzy. Kizzy is an optimized version of Ruby Enterprise Edition by Twitter developers. The Twitter team substantially extended my work. It's cool. But Kizzy will be also rejected. I'm so sad. Okay, next, I created Lazy Swift DC at Ruby Kaigi 2008 and 2010. Traditional mark and sweep DC executes mark and sweep atomically. Ruby application stops doing DC. This is called stop the while. In lazy sweeping, sweeping is lazy. Each invocation of the object allocation sweeps Ruby's heap until it finds an appropriate free object. This improves the response time of DC, i.e. the worst case time of DC decreases. You can use lazy swift DC since Ruby 193, but I omit the details of lazy swift DC because it's not the main topic in this my presentation. Finally, I created parallel marking DC at Ruby Kaigi currently, and it's the main topic in this my presentation. Okay, now I'd like to introduce today's topics. First, why do we need parallel marking? And what to consider? How to implement? How much did performance improve? First topic is why do we need parallel marking? This is CRuby's current CC. This means CC operates on only one core. In multiple environment, other cores don't help DC. So this is alone. We should run DC in parallel. Okay, first, let me explain a few DC-related concepts. DC collects all dead objects. What is a dead object? A dead object is an object that is never referenced by the program. In DC terms, we say that dead object is unreachable from roots. What is roots? Roots is a set of pointers that directly reference objects in the program. For example, Ruby's local variables and Ruby's global variables, and so on. For example, we execute this Ruby program. In this case, B is unreachable from roots, so it's a dead object. Please remember that DC collects objects that are unreachable from roots. Next, let me explain the current CRuby DC algorithm. CRuby DC algorithm summary. CRuby adopts the mark and sweep algorithm. Corrector works in separate mark and sweep phases. In the mark phase, corrector marks live objects that are reachable from roots. For example, we execute this example program, A equal new array, then we push new array to A, and push string A to new array, and push string B to A. Finally, we pop string B from A. So this is the object relationship is created by the example program. Please note that the reference from array A to string B is cut here. Then we execute this stat. In mark phase, all reachable objects from roots are marked. So string B isn't marked because string B is unreachable from roots. Ruby heap is divided into blocks. These blocks are called Ruby heap blocks. And Ruby heap blocks are divided into objects. After marking, all objects are categorized as data object or live object. Here, black object signifies a marked object. Gray object signifies a unmarked object. In the sweep phase, corrector sweeps a data object. That means unmarked. That means unreachable from roots. In the sweep phase, corrector scans the entire Ruby heap. Corrector unmarks object if it's marked. And corrector sweeps object if it's not marked. In this case, string B is swept. After sweeping, this is completed. Okay, now let me explain the characteristics of C with ZC. First characteristic is the stop-the-word algorithm. Next is single-thread execution. Today, I'd like to talk about single-thread execution. Recently, PC has multiple processors, but this executes on single thread. Other cores don't work during ZC. So what a waste. How can we fix this? We should use parallel marking. What is parallel marking? Corrector runs several marking processes in parallel by using native threads. We will be happy on multiple machines. This shows a flow diagram for parallel marking. The line at top of this diagram is the Ruby application execution flow here. Following lines the Deque execution flow. After Ruby application is stopped, this is invoked. And this executes in parallel by using native threads. In this diagram, this has 3 marking threads. By the way, why not perform sweeping in parallel? The sweeping is much faster than the marking. So you can see Koichi's research if you are interested. So mark phase improvement equals this improvement. And we already have the lazy sweeping. Okay, next topic is what to consider when implementing parallel marking. Actually, we should consider two problems. First problem is the workload balancing. How can we divide the marking task into subtasks? I try to think about a simple approach. The approach is that one branch of root is marked by one thread. A branch means an object which is referenced from root and its children. A branch and B branch are shown here. Usually there will be many branches, but only two are shown here. A branch is marked by A thread, and B branch is marked by B thread. So this means marking of single branch is performed by a single mark thread. This means tasks are distributed to multiple threads. The task of marking the entire heap is divided into several tasks, each marking the single branch. This seems to be no problem, but actually this solution suffers from the workload problem. This illustration shows each marker thread has a branch. Each thread doesn't know what the other threads are doing. For instance, if A and B finishes work early, then they will be stop doing anything like this. I think machines should work forever. So I think A and B should steal other threads tasks. Let me introduce parallel marking with task stealing. If A and B finishes work early, they steal C's task. This is called task stealing. The next problem is wait-free algorithm. What does wait-free mean? A wait-free program does no blocking execution, and it guarantees path-thread progress. Why is wait-free important? Amdahl's gives an answer for this question. Amdahl's law is used to find the maximum expected improvement to an overall system when only part of the system is improved. Amdahl's law is used in parallel computing. If parallel portion of the system is X% and number of processors is Y, so how much speed up can we expect? This graph shows the overall speed up of system. X-axis is a number of processors. Y-axis is a speed up of system. For example, if number of processors is 8 and parallel portion in the system is 95%, then execution is 6 times faster than with 1 core and 0% parallelization. But if parallel portion is 90%, then non-parallel portion is 10%. So this system can be speeded up by a maximum of a factor of 10, no matter how many processors you use. So if you have any sequential parts, then they may be bottleneck on multiple processors. It wasn't expected. Okay, the conclusion so far. We should consider how we can efficiently balance workloads. So we use task steering. We should eliminate non-parallel parts by using weight-free algorithm. Okay, next topic is how to implement parallel marking. In task steering, threads steal tasks from each other. Task steering is achieved with Arora's Deque. Arora's Deque. Arora's Deque, Deque stands for the double-ended queue. In Arora's Deque, the Deque contains tasks as elements. It's a weight-free data structure. Arora's Deque has only 3 operations. First operation is pop. Pop operation removes the bottom task from Deque and does it. It's same with pop method behavior, you know. Second operation is push. Push operation appends the task on the bottom of this Deque. Third operation is shift. Shift operation returns the first task of Deque and removes it. This shows mark worker 1 and 2 and 3. Each mark worker corresponds to a single mark thread. Each mark worker has a single Deque like this. So only the owner worker can call pop and push operations. And workers can call shift operation to steal from other workers' Deque. In this case, worker 1's Deque is empty, so worker 1 calls shift operation of worker 2's Deque. Then worker 1 gets the task of worker 2's Deque. This is task stealing. Perhaps you think doesn't shift operation have contention problems? Much thread may call shift operation of same Deque at the same time. And shift operation and pop operation could be called at the same time when Deque has only one element. But Arora's Deque avoids these contention problems. Shift operation is serialized by using compare and swap operation. And this serialization doesn't use a log. It's a weight-free. But I omit details of the implementation of the serialization. For the sake of this presentation, let's assume that Arora's Deque avoids contention problems. Okay, I'd like to summarize what I have said about Arora's deck. A simple data structure for task steering, and each worker has single deck. And steering is weight-free. Yeah, how to use Arora's deck in parallel marking? My first try is that a task is an object. Let's say that worker A has a branch that is composed of 4 objects. We start by marking A and pushing it to the deck. And pop A, then we pop A from deck, and mark B and C. Yeah, B and C objects are A objects' children. Then we push B and C to deck. Then we pop C from deck, and we mark D and push D to deck. So finally, we pop D and B. Okay, this is branch marking. So next question is, how do you steer? Suppose that worker 1 has task B and C, worker 2 has no task. Worker 2 steals task B from on worker 1 by using shift operation. Let me summarize. Marker uses Arora's deck as a marking stack. A task means an object. The granularity of the task is very fine. This is naive implementation. So I implemented this approach, but it's slower than original DC. So I'm very shocking. I fell into the pitfall of parallel processing. So I thought, why is it slow? The answer is that pop and push and shift operations are called frequency because Deque has fine-grained tasks. The overhead is too big. So how to fix this? We can make the tasks less fine-grained. A task is a branch. Now, all branches in rules are divided roughly among the decks. Worker A has branches on deck, like this. Worker B has branches too. So now the deck holds only the top node of each branch, and each worker traverses the rest of the branch without using the deck. So when the deck is empty, the worker steals a branch from another worker. In this case, A's deck is empty, so A steals a branch on B's deck, like this. This approach has good point and bad point. Good point is number of calls to Deque's operation was reduced, so marking speed of the worker is improved. However, coarse-grained tasks decrease parallelism. So why do coarse-grained tasks decreases parallelism? tasks may involve a large branch. So if an object in B's Deque branch has many child objects, then A can still eat while B is marking at the large branch. So the worker needs to treat large branches as special cases. As a matter of fact, almost all large branches hold large array objects and large hash objects. Actually, each marker has a special deck to manage them. A marker divides them into fixed-size tasks. For example, first 10 elements of the array, next 10 elements of the array, and so on. By doing this, other workers can still divide tasks. This improves parallelism. Okay, I'd like to summarize what I have said about task-steering implementation. The naive implementation was slow because grain of the task was too fine. I changed a task to mean a branch in rules, so the grain of the task become coarse. It's faster. Okay. Next topic is how much did performance improve? These are my machine spec. My machine has only two cores. And parallel marking uses 4 marking threads. First benchmark program is make benchmark. This is the benchmark which used in CRuby development. Okay, this shows the result of the make benchmark. This shows the rate of increase in the performance when using parallel DC compared to the original DC version. Each line is the result of a single benchmark. If the line points upwards, it means that performance increased. But if the line points downwards, it means the performance decreased. Okay, why does this seem so slow? I think it's affected by parallel marking preparation. For example, creating marking threads and allocation of deques. And in most of the benchmarks, the mark target objects are few. In this case, parallel marking cost is expensive. Okay. Next benchmark program is make rdoc. Make rdoc generates the Ruby documentation. This benchmark measures execution time and this execution time of make rdoc. Actually, it takes about 80 seconds on my machine. But in fact, 30% of that time is spent on DC. How much did performance improve? Original DC takes 26 seconds, but parallel DC takes 16 seconds. it's 10 seconds faster than the original ZC. So all ZC time is improved by 40%. Yeah, so fast. In many core environment, I expected we get a large improvement. For example, 8 core and 16 core and more. But my machine has just 2 cores, I can see it. I explained that best case for parallel ZC, if the objects are many, in this case, marked targets are also many. And if the objects are long-lived, for example, in a server-side application. Okay, demonstration. I want to show the performance improvement with parallel ZC. This demonstration is video game style. Yeah, let me explain about this game. The game title is Super Narihiro ZC. Yeah, it's a traditional side-scrolling video game. You should collect the garbage if you find it. Seeds popped from G block when you headbutt it. When you reach the goal, okay. Okay, reach a goal. Game clear. Yeah, and character has hit point. When DC runs, the character loses hit point while waiting for the DC to finish. We must reach the goal before hit point run out. Okay, this is running in fixed intervals, and a lot of objects are generated to increase this is burden. This is burden equals game level. Original DC pause time is long. This game will be difficult. But parallel DC pause time is short. This game will be easy. Okay, let's try. First demonstration is original ZC version. Okay. Time up. Yeah. So difficult in original DC version. But next demonstration parallel DC version. Yeah. Okay. Easy. Let's compare the average times DC. Yeah. In original DC version, like this, DC average time is 48 milliseconds. Next, in power DC version, DC average time is 34 milliseconds. I have prepared some additional figures in advance to show you the performance increase in percent. Okay, it's faster than the original DC. Finally, I'd like to talk about the remaining problems for power of DC. Windows OS is not supported because Mac Worker uses pthread as native thread and uses some DCC built-in functions. But I support for Windows eventually. And increased memory usage, size of one Deque is roughly 32 kilobytes. But generally, multiple machines have plenty of memory. I think it's okay. Conclusion, I implemented power marking DC. DC was improved. I report to Ruby code soon. But power marking has some problems. I'll fix these. Okay, you can get source codes if you are interested. Acknowledgments, the foreign people helped me make this presentation. I couldn't do this without you. Okay, that's all for my presentation. Thank you for your attention. Do you have any questions? Pretty short and simple questions. Okay.
How configurable is your parallelized PC? Are you able to specify the number of cores to use in doing the market sweep, or does it always take up the number of cores available on the machine? Are you able to
Yes, 設定できます。Yes. はい。ですね。英語で、日本語でいいですか？いや、そのマークビットを立てるだけなので、衝突しても問題ないっていうことですね。 Oh.
Generational BC not included in Ruby 1.9 or Ruby 1.3? Why was it not included in the original generational BC that you implemented? For what reason was it not included in Ruby 1.9?
You mean that the generation one in
In 1.2.
Long right? Oh.
Long life, yeah. Oh, yeah.
It's very long story. Oh. Okay.
It seems like this is best suited for many objects off of a root. Have you thought about using the more traditional stuff for that and just use Deque for bigger branches? Is that, I noticed all the down arrows in your performance graph. Support both. A hybrid approach might fix the make benchmark speed. You don't know how big the tree is until you convert it. Yeah, part of the problem. Sure. You have to figure it out and switch modes. It would be tricky.
Yeah, if you use the type of branch previously, you know.
But he's already detecting big branches and putting them in a different queue. And I was thinking you could do that detection in a more traditional sweeper and then say, oh, this one's big. Put this in the queue for multiple.
大きな枝をあった時点で、それを他のスレッドに渡すっていうアプローチっていうのはどうだろうか。
枝のサイズってわからないんですよね。
だから、今、そのタスクスティリングみたいな感じで取っていくときに、その枝を渡すことになる。In general, the size of the branches doesn't know, so it's quite difficult to say that this branch is big. So
You have to abort after you've got into it and change algorithm picking.
So you have to change the algorithm. Or I don't know how to do it really previously.
Maybe Ruby Kaigi 2013.
Any questions? Okay. Thank you.